x to the fourth, and then minus 84 and x squared. And I know everything about the function, so I know how to adjust the viewing window. I'm not gonna need anybody to tell me what to do. So I'm gonna say between -4 to 4 if you want, with a scale of 1. Definitely -150 or maybe even 160. I don't need to go too high. 10 is good enough with a scale of 10. And I know the graph. It's coming. That's it. Very difficult to identify. I don't even know if the calculator, I haven't, these are the newer calculators. I don't think that you can determine the inflection point with the calculator. You still have to do all the work. I don't know. Maybe you find a way. I have not looked. I don't need it. But if you find a way, please teach me so I teach other students. Very good problem. Moving on. Anything else from me? Do you have other questions from homework or otherwise? Okay, then. So now we're going to explore how to graph rational functions. They are the most intense, if you want, because they have a lot of important information that we don't see in other functions like polynomials, for example. I'm on page 231. Feel free to choose any problem. Let me choose the first one, and then you will choose the next one. On page 231, I'm going to start with a simple problem. Let's look at 44. On page 231, and the function is f of x equals x minus 2 over x plus 1. Everything the same, but we have, in addition to what we've seen, we have some characteristics specific to rational functions. But the table is identical. We're asked to do the same thing. Discover everything you can about the function from everything possible and just graph it. Few things here that we have to look for, which we have not looked for before, are what is called vertical, horizontal, or slant, also called oblique asymptotes. Now, vertical, any type of rational function can have a vertical asymptote. We'll get to that in a minute. Not all rational functions have horizontal, and not all have slant. If they have slant, they cannot have horizontal. If they have horizontal, they cannot have slant. If they have slant, they cannot have horizontal. These two are mutually exclusive. Either this or this. So for now, we're not going to discuss about this. We're going to finish up a couple of rational functions and graph them. But then I will specifically look for examples for slant. But for now, we're going to focus on these two. Okay, so I'm looking at this function, and I know immediately that x cannot be which number? Can anyone tell us what is the restriction of this function? What x cannot be? -1. Excellent. I think I heard -1. If I didn't, then I'm imagining things. So if the function is undefined at -1, automatically its derivatives will be undefined at -1. Because -1 is because x plus 1 does not go away with a factor of x plus 1 from the top. I cannot simplify x plus 1. I will give an example in which we can simplify. But since I cannot, then I know that x equals -1. I'm going to put it in my table. is a vertical asymptote. What does that mean? It means the function is not defined there and the sides, I will have to determine limits here now. The sides will go either to positive, negative, or both positive, or both negative, or the other way around. So I know that these will be infinities. Now, I will also plug in 0 in the function. 0, 0 is negative 2 over 1, which is negative 2. When I try to find x-intercept when y equals 0, I have x minus 2 over x plus 1 is 0. Automatically, I know a fraction is 0 only when the top is 0. That makes x equals 2. Be very careful. All these numbers have to be in ascending order. And again, you cannot prevent this from happening. Sometimes it will be so crowded that you have to redo the table, like I did. It's okay. So now, in order to finish filling up this, I have to determine these limits. And there is nothing else I can discover about the function from the function itself. This is it. Okay, that's why we studied limits. That's one of the reasons, not the only one. So I'm on page 5. So limit as x approaches infinity from x minus 2 over x plus 1. Then limit as x approaches negative infinity from x minus 2 over x plus 1. And then limit as x approaches negative 1 from the left from x minus 2 over x plus 1. And finally, limit as x approaches negative 1 from the right from x minus 2 over x plus 1. When I plug it in, because I have to plug it in, I get infinity over infinity in both cases here, which I like. Why? Because of L'Hopital's rule. L'Hopital's rule says that if I try to find the limit of a ratio and I get infinity over infinity or 0 over 0, I can differentiate the top and differentiate the denominator, and I'm done. Same thing here. This will also be 1. That means that y equals 1 is a horizontal asymptote. What does that mean? The function, if this is y equals 1, oops, I didn't mean that, the function will get closer and closer to infinity and closer to negative infinity. From below or from above, we don't know that yet. Finally, I need to determine this. When I plug in negative 1, the numerator is negative, but the denominator is 0. When I plug in negative 1, the numerator is negative and the denominator is 0, which I know, no hope. Meaning it's either infinity or negative infinity or DNE. If I have a number over 0, that is automatically one of these three. Okay, fine. So now I'm going to plug in negative 1 from the left, negative 1.1. This becomes negative. The numerator is negative, so this will be positive. Negative 1 from the right will be negative 0.9. This is negative. Negative 0.9 plus 1 is positive, so this becomes negative. I know for sure that x equals negative 1 is a vertical asymptote. So the left is infinity. The right is negative infinity. Finished with the function. All this work was to fill this in. Now I have to fill this in. And I have to find f prime. The top prime is 1 times the denominator minus the top times the denominator prime, which is 1, over x plus 1 squared. So x plus 1 minus x, but plus 2 over x plus 1 squared. I like that very much. It's 3 over x plus 1 squared. Never 0. And never undefined. Why? It's undefined at -1, but who cares? Even the function is undefined at -1, so no critical numbers. No critical numbers. Nice. Always, what kind of sign does this have? Because I still have to put the sign in. What is the sign of 3 over x plus 1 squared? Anyone?
Is it positive?
Always positive. Which means the function is always increasing. Thank you very much. Now I have, this is my moment of truth. This is when I catch my mistakes. And that's why when I say, oops, go back. From 1 to infinity increasing, yes. From -infinity to -2 increasing, yes. From -2 to 0 increasing, yes. From 0 to 1 increasing, yes. Good. Second derivative. And you know me already. First derivative is for me 3, x plus 1 to -2. So the second derivative, I bring down -2. I subtract 1 from the power, and I multiply by the inner function prime. Who cares? It's 1. Never 0. And now I have to study the sign. To the left-hand side of -1, this quantity is negative. Just plug in -5. -5 plus 1 is -4. -4 cubed is negative, and there is a minus here and a minus here. So obviously this is positive. So it has to hold water, so to speak. If I plug in 0, I get 1. 1 cubed is 1. 6 over 1 is positive, but there is a minus in front. It doesn't. The only thing that doesn't fit here is the symmetry, but it's not symmetric because the function that has a vertical asymptote at -1 and does not have it at 1 cannot be symmetric. That's it. Done. When I graph a function with asymptotes, I have to graph the asymptotes first. I don't care about any calculations except my table. Nothing else matters anymore. So here's the graph. We start with asymptotes. -1. And y equals 1. They are not part of the graph. That's why I'm not going to graph them as solid lines. And now, from it's opening up, increasing from 1 to infinity, from the horizontal asymptote to the vertical asymptote on the left-hand side of it. No problem. Piece of cake. Opening up from approaching 1 to approaching infinity on the left-hand side of the vertical asymptote. On this side, I have 0, -2. And I have 2, 0. And the table says opening down all the time, all the way increasing from -infinity on this side of the right-hand side of the vertical asymptote, cross the y-axis at this point, cross the x-axis at this point, and make sure you approach 1. Okay, no problem. Do not touch the asymptotes. Can I determine the range? Of course. How do I determine the range? Yes, 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 yes. No. Yes, 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 yes. So everything but 1. So this is the procedure of graphing a rational function, looking at everything that we've studied so far. Any questions? I hope you appreciate the importance of a table, not necessarily mine, but a table. Anything you invent your own, create your own, make adjustments to this one, amend it, do whatever, but you have to have everything summarized. You can imagine, how will I graph without summarizing everything? I will have to look at 3 pages or 2 pages of work. Where? What? How do I start? Good. Would you like to choose the next one, or I will show one with a slant asymptote and one note here I would like to mention. Note: a rational function can cross a horizontal or slant asymptote, comma, but never ever a vertical one. Ever. So I would like to present an example with a slant asymptote, and so the slant, when you're ready, and you'll tell me, and one example with a hole in the graph. So please tell me if you'd like to choose another type of problem, another type of rational function, or we move on to what I would like to present.
50.
Which one? I couldn't hear you. I'm sorry.
50.
50. 50. Perfect example. Thank you. It's a very a good example. Thank you. So f of x, I don't know the graph, but by simply looking at what we see here, it's a very good example. I would have probably thought to pick this. Okay, very good. So it's 50 on page 231. Let me start a new